landscape mode for this would probably be best.
What does that mean?
Means turn your paper this way. Landscape, portrait, turn to landscape. Sideways. Title it Electromagnetic Spectrum. Write it down. Electromagnetic spectrum. Okay? On your paper. On your sideways oriented landscape mode paper. What? I do not. But I'm sure somebody in here would probably grant you permission to borrow one of theirs. All right. So let me ask you a question. Can we, with our flesh and blood eyeballs, see the electromagnetic spectrum? Yes. A part of it. Okay? Have you ever heard the term visible spectrum before? Well, now you have. The visible spectrum is the part of the electromagnetic spectrum that we can actually see with our optic nerve retina thing. Okay? And you probably remember kind of what it's called, right? Or the pieces of it. Elementary school, do we remember the first name, middle initial, last name of the rainbow? Roy G. Biv, good. Roy G. Biv. The R is?
Red.
O is?
Orange.
Yellow is?
Yellow.
Yellow is yellow.
G is?
Green. Green.
B?
Blue.
I?
Indigo.
Indigo. And V? Violet. You can see, unless we've got a vision disorder, right? You can see Roy G. Biv and all of the shades of them, right? The human eye is able to see lots of shades of red and orange and yellow. And most of all, shades of green. We can see lots of shades of green, blue, indigo, and violet. So if you go to Lowe's or Walmart or Home Depot, wherever you buy your paint from, they've got that section of wall with all the swatches you can pull and take home and put on your wall. I'm like, I don't like that one. We can see all those and many, many more. Lots of shades in between, okay? That's why they're always inventing new names of colors with weird names. You know what I'm talking about? Like ghost shit. Okay. That's the actual color. We see those. But with our bodies, did you know that we can detect more? With no technology whatsoever. Can anybody think of another wavelength of light of electromagnetic spectrum that we can sense?
UV.
UV.
Ultraviolet radiation.
Ultraviolet. Good job. All right. So UV light. How do we sense that?
Sorry.
Not the heat.
The radiation.
The brightness.
Nope.
Color.
Nope.
Smell.
Oh, yeah. Actually, I like that. The smell. You can smell your burnt flesh after you've been burnt, can't you? It's like, no, that's a bad day. Guys, the UV, your sense for the UV is a delayed reaction. Because once your skin is visually, damaged, it's too late. As it's being damaged, you don't notice it right away, do you? You don't notice it until it's too late. Like, I'm fine. I was like, oh, dang. And then you're taking a shower that night or the next day, and it's like, oh, I got to take a cold shower because it's warm, but it feels like it's burning you, right? Or if it's a bad burn, you're laying in bed, and the heat feels like it's re-radiating off of you, like your skin stored the heat from the sun like a battery, and then you're just hot, right? Anyway, aloe vera, that green gel. Oh my heavens, that's your best friend if you burn yourself. Okay, so UV light, we can sense it, but it's a delayed reaction sensor, I guess. But there's one that goes along with this on the other side of the visible spectrum that we can feel right away. That might give us a warning that we should be careful.
Heat.
Heat.
Pain.
IR. You guys ever heard of IR?
Ultraviolet.
Infrared. Good. If you want to spell that out, it's I-N-F-R-A, red. Infrared. And infrared radiation is kind of useful. Obviously, you feel that warmth on your skin in the sun. That's what you're feeling. But also, if you've got a remote control that has like this light bulb looking thing, okay? It looks like a light bulb, but if I can press it. I can point it right at your eye and press it. Do you see anything? You don't see any light coming out. Look. Is there any light coming out of there?
You do. They're red.
Yes, there is, because it's changing the volume on the TV.
Oh, I was like,
But you can't see it because it's infrared light. The TV sensor can interpret the signal carried by that infrared light. Now, another cool thing about infrared is we can shift, if we have a computer program, if you've got sensors that can pick up infrared, and you run it through a computer program and shift it, you can make infrared appear visually on the computer screen to you as if it's red. Makes it very useful for certain imaging. Yes. Sure. All right. How you leaving? All right. Now, continuing, we're going to go, if you go further this way, the wavelength gets shorter. If we go further this way, the wavelengths get longer. If we go all the way to the longest category, they're called radio waves. Has anyone ever heard of radio?
yes.
Okay.
A movie?
Radio waves. We started really playing with these things as far as scientists did back in the early 1900s, late 1800s, early 1900s. And by the 30s, they were actually sending out radio waves and getting a signal back. Like it was, the waves were bouncing off objects and then coming back, and they could receive those signals. Okay, so they fashioned an invention called radar. Anybody ever heard of radar? Yeah, aviation big time, right? So they send out radio waves, they bounce off of aircraft, come back to the antenna, and then the computer apparatus, I don't know how it works technically, it puts it on a screen for you. So you can see and read out of information, how high is it, how far away. If you're sending them out often enough, you can figure out with the direction of travel, how quickly they're traveling, which is useful if you're trying to defend your island like the British were in 1940, right? Battle of Britain. And so they could use the radar to see German bomber squadrons coming in to bomb Britain. So they'd be able to time their response. They'd be able to tell the RAF, the Royal Air Force, hey, send up the fighter squadrons at this time into that direction. Because the fighters have limited fuel on board, yes? Yeah, they didn't have like aerial refueling back then, okay? So it takes a while to climb up to the altitude that the bombers are flying at. And you can't just guess when they're going to get there because you might miss it and you only have a couple minutes to shoot at them, right? So anyway, they come up with this radar thing. While they're fine-tuning radar, they play around with different wavelengths of radio waves. And they shorten it to the point they're so short of radio waves, they categorize them and they call them microwaves. And they notice that these microwaves, when they hit certain things, the waves, that wave energy is converted to heat. So the molecules of the object that the microwaves hit get vibrated and the temperature increases. Does that make sense? You guys know where I'm going with this, right? So by the late 40s, scientists had a pretty good understanding of how microwaves could be used to heat up beverages or food. So by the 50s, you were starting to see these go into restaurants. So they could quickly, big units, these things were huge, right? But they could quickly heat food. By the 60s and 70s, they had shrunk them down to a size of a box that you could actually put in your kitchen. So by the 60s and 70s, you start seeing households that you could actually afford to buy a microwave for your kitchen. Has anybody ever looked into their microwave while their food or beverage is warming up? Okay, good. But why didn't, if you're that close, wouldn't the microwaves like heat up and disfigure your face? Why not? There's a screen. You're the first person all day that has said, well, yeah, there's a screen there. So that metallic screen on the inside of the glass, the microwaves can't get through the screen. The screen is sized so that that microwave is a certain wavelength and it has a certain height to the wave. It can't get out the screen, but you can see. Yes?
How come when you put like a fork in there, it goes down?
Yeah, because the metal is going to reflect that energy. My favorite was my youngest daughter put in, you know these like hamburger wrappers that are metallic? So it's like a paper with a metallic film on it to hold the heat in better. She put that hamburger in there, and by the time I got to the microwave to take it out, it was on fire. Yeah.
One of them
Put a fork.
tinfoil in there, and I turned around.
Sparking and everything. Yeah, absolutely. That's fun. Don't do that.
I already have.
Okay. So that's that side. On this side, by the way, guys, obviously you could get hurt by a microwave, okay? But there are protections. You guys understand how to not hurt yourself with a microwave. But this is more where we'd be concerned with. UV over causes more damage to like people, more of a risk. So UV sunburn, right? How about X-rays?
Well, you gotta wear a vest.
Yes, when you go to the dentist or the doctor, they're going to X-ray you. They're going to try to be as focused as they can, right, to where they need to image. And the X-rays are so energetic they can go through your soft tissues. They can go through your skin. They can go through your muscle. They can't penetrate bone very well, though. Okay, so it's perfect for imaging your bones. Those X-rays, though, because they are so energetic, they can damage your organic tissues to include your genetic information. So specifically, they usually put those lead aprons over your reproductive organs, right? Because they don't want to sterilize you by accident or cause birth defects in your offspring later on. Does that make sense? Because the genetic information, the DNA, can be damaged by the X-rays. In the early days of X-ray technology, they would play with it like it was a toy. They would set up X-ray machines like projectors. So they would have X-ray generators, like a light bulb, essentially, and they'd have people walk by, and on the screen behind, you'd like see what their bones looked like, right? Like you'd be able to see, not behind, but you'd be able to see what they look like, just their skeleton. But they were overexposing people to X-rays. They were overdosing. And some of the first people that worked with it ended up like dying of cancer and stuff like that. So that's dangerous to us. And then farther over, the furthest on the shortwave side you can get is gamma rays. And gamma rays, of course, produce things like the Hulk, right? And Captain America with the serum. You never seen Captain America? Oh, all right, that's fair enough. But in reality, yeah, it can cause serious problems. Gamma ray bursts from like supernova explosions, if they're directed at Earth, basically if you're on that side of the planet and we're close enough, you're done. Hopefully you're like underground or something, but the atmosphere, the ozone would be destroyed. It'd be a bad day. Very bad day. Gamma rays.